Hello, and welcome to the October meeting of Tahoe Silicon Mountain with the topic, how to use the brain to build artificial intelligence. And as you can see from the audience here, this is really a very popular topic. I also want to welcome everyone who is watching online. Thanks to TTC TV, we can actually do this. Before we start and introduce our speaker, let's make sure we honor our sponsors, and I hope that will also motivate maybe a few more people to also become sponsors. But Tim, you want to say who is helping us?
Yeah, definitely. Yeah, everything we do, every month we meet here, the facilities, the pizza for $5, can't beat that. This is all put on by our sponsors. I mean, they really keep this group running and growing. So I definitely wanted to thank our gold sponsors. So first of all, we have New Leaders. They're a software development company that streamline business processes. They can automate business workflows, SaaS integrations, anything you need to automate through technology. So thank you, New Leaders. Clear Capital. Clear Capital is the leading provider of real estate valuations, data, and technology solutions to mortgage lenders. Thank you very much, Clear Capital. And Holland & Hart, they're a solution for custom-tailored legal representation. They have 60 attorneys in Reno, Carson City, and Vegas. So if you need any kind of legal representation, please get a hold of Holland & Hart. And then, of course, our community partners. So the Truckee Chamber of Commerce, anyone that is a member here can go to any Truckee Chamber event for member prices. TTCTV, if you're watching this, then that's what they are. Thank you so much to them. Use Pay It. Use Pay It is what we're using. If you paid today, we're using it on the tablet to take payments. It's a payment solution for local businesses. And then, obviously, Pizza on the Hill to provide us with these facilities, pizza, salad. So thank you to all of our community sponsors. And if anyone is interested in sponsoring one event, specific event, or long-term sponsorship, please talk to me after this. We're always looking for new sponsors. So
we are actually looking for two things at the same time. One is new sponsors, and really we are running a bit of a tight ship. So I really would ask if someone wants to do something good, even if it may not double your sales next year because of the promotion, but you're doing something good for the community, consider doing it, even for a couple of months. I would hate to cut down on what we're offering here. Number two, if someone has some time to help us find more sponsors, that would be wonderful, because Tim has helped us a lot, but he can't do it all, and he needs, and we all need help. So if you want to work with a great team, we're all friendly and have a good time together. So please talk to me afterwards. So with this, let's make sure we honor our speaker for tonight, Gunnar Newquist. I always have problems with last names because I never say them, but here I do it once. Who is very special because he's not one of those guys who have a career somewhere where usually you work in tech and then you come semi-retire here and still do a little bit of tech things on the side. No, he actually came to ski, got a house just around the block here at Davis. He then moved to Squaw, even more hardcore skiing, but then also went back to school and did his graduate studies and then his Ph.D. in neuroscience at UNR in Reno. And then also did kind of start going to other universities internationally, Paris, to study more, and is now the CEO of a local AI company, Brain2Bot. So I like those examples that, hey, you can do cool things, and you don't have to move to Palo Alto or San Francisco to do that. And I was kind of thinking about why am I so excited about this topic, and I see there are a lot of people excited, and a lot of it is very personal. So artificial intelligence is something we've been talking about a lot in our family. Actually, my oldest son, he spent some time last year to work with MIRI, the Machine Intelligence Research Institute, to kind of think about ways how to limit potential damaging and dangerous impact of artificial intelligence. My younger son, he just told me that he joined the Neuroscience Club at college, at Cal Poly, and he's thinking about maybe doing this as a minor. So AI and neuroscience, this is really our family. And finally, I will have something new and interesting to talk to my sons where I can actually maybe hold water for a little bit. So let's see. And of course, like everything that has to do with artificial intelligence will change our lives in major ways. And so it's very cool, and it's an honor to have you here to talk about an example where we do another step forward. Thank you for being here.
Thank you.
I
have my own mic even.
You don't need
Thank
mic.
you.
But talking about mic, if you have a question, don't just yell it around the room, but raise your hand and somebody will hand you a microphone, because otherwise nobody outside of that room will hear that question. So that's why this mic is important. Thank you.
Okay. I'll move to the tile slide. So first of all, I'm excited about all the turnout, especially for the younger people here in this audience, because to actually really propel this field forward, we really need young talent. The older you get, the harder it is to come up with completely new, groundbreaking ideas. So we need somebody that's kind of breaking the rules and wanting to try something completely different to actually push this field farther. And as far as the interest, I kind of feel like this is probably the, artificial intelligence and also neuroscience. I can't really imagine much more of an exciting field for just about anything. I mean, it rivals that of skiing even for me. So hopefully that resonates with this crowd here. I would like to actually start this with a question, a very simple question. What is the most complicated object in the known universe? The brain? Any brain in particular? The human brain? Whose human brain? So this is the typical answer. This is the answer you'll get from the Allen Brain Institute and all the top neuroscientists in the world. But let me present a different perspective. This is a typical human brain, about 1.3 kilograms. Here is a sperm whale brain. It is literally 5 times the size, and it's made up of cells that are just like the human brain. So there's a possibility that maybe the human brain isn't the most complicated thing in the universe. So just let that, think about that for just a little bit while we go through this talk, and I'll come back to this. I'll tell you why that's important later. So what were we actually talking about? Artificial intelligence. And this has a long history starting in, I don't know, the 30s, maybe even earlier than that. And a group of academics kind of got together. Some of them were computer scientists, some of them were psychologists, and they said, I bet we can build a machine that acts like a human. And so this notion of artificial intelligence took off at a time when people were building everything. Artificial back then wasn't really the bad word it is today, where you think about artificial ingredients and all this making that isn't good for us. Back then, they thought that artificial intelligence or anything artificial was better or could be better than what is actually produced in nature. So they created this field, but we have to ask, what does that even mean? So let's give you a definition here. Artificial intelligence is the capacity of a computer to perform operations analogous to learning and decision-making in humans. And what that encompasses today, we have a Venn diagram that describes all this, all these separate fields that are all complicated and interrelated. But these are all things that humans do in some respect. Where I'm going to start directing this talk is actually kind of pushing out towards this fringe of neurocomputing. That's making the brain, I should say, making a computer act more like a brain. So, this is what we're talking about. What do we have today with AI? This are some little clips from the DARPA challenge. It's where they make the best robots in the world try to do specific tasks that a human can do. And these things cost sometimes tens of millions of dollars, and yet they're still falling over, right? So this isn't quite what humans are capable of. Well, some of us, but I mean, some of us do a little better, right? So what is AI good at? It's not really walking, but what is it? Repetitive tasks. AI for a long time has been striving to get engineering of mass production to a science. So these car manufacturers, they can do the same exact movements faster than humans, more precise, and cheaper, right? And today, artificial intelligence isn't just, doing the same thing. It can learn to be better too. It can learn the optimum path to get the best efficiency out of its movements. So that's really good. Now we're getting into also object and facial identification that is so good that you can detect anybody on Earth as long as they have pictures of them. You can also detect the words. You can just talk into your phone. Everybody knows this. You can talk into your phone and say, a sentence, and it'll print right there. It knows exactly what you said. And it's pretty close to 100% accurate nowadays. Narrow tasks is where AI really excels. And a narrow task means that it's one specific function. This is a picture of something that happened this summer. This is a game of Go, which is the most complicated board game in the world. This game was between Google DeepMind, a machine, and a world champion of Go. Now Go, Google DeepMind, AlphaGo, made a program that does the moves, and this man here actually moved the pieces and was able to beat one of the world champions at this game. So this was a huge step forward. But it can only do this game. This program can only play Go. It could not even move its own pieces. It needed to have a human surrogate to move the pieces. But that's still a very big step forward because this wasn't possible just a few years ago. It's not chess. It's way harder. This is the thing that I'm really excited about with the big data. Being able to find patterns like this. What is this? This is a map of Europe, and this is a genetic principal component analysis that tells you exactly, based on the genetics of the people in this region, where they live. It can predict to a few hundred kilometers, based on your genetic sequence, where you should be living in Europe. So these different colors are different countries. So these people right there, they said, oh, you sequence a bunch of genomes, and they say, oh, you probably live in Ireland. There you are. These guys were Spain. This is Portugal. And you see, it actually replicates the actual map of where these people live. And this is unbelievable. They used 500,000 different gene loci and thousands of participants to come up with this graph. This is not something that humans can do. That's just too much data, right? Is that all clear for people? Make sure you ask questions. I'm trying to be general, but if you want more detail or more explanation, please let me know. So genetics match where people live. Now, what is the brain good at? So this actually is repetitive behavior, right? This looks really funny to us when you're dancing because people really can't do the exact same motion over and over and over. So this is actually the opposite of what humans do. You have a little bit of variability every time you try to do the Carlton dance. Instant recognition and response. So you look at you put yourself in the middle of Times Square in New York. You can identify everything in this picture and know exactly what to do with it. You see Coca-Cola, you get thirsty. Or, well, some of us get thirsty. You know what to do with a Coca-Cola, though. If you're sitting in the crowd here and you're just, around the masses, but somebody jumps right out in front of you, you don't have to think about it. You immediately jump back. So even with all this distraction, you know exactly what to do immediately. This is very difficult for computers. Doesn't matter how complicated it gets either. Flexibility. Have to show a ski picture here. This is actually Mike Wilson doing a backflip off a cliff. He could have gone 5 miles an hour faster, landed the backflip just as easily as if he went this way. He could have done a 360 off of it. He could have just gone straight air, landed almost every single time, no matter what the snow condition, because we can just adapt on the fly to every single little variability in this scene here. And we don't have to experience every single type of jump that way to be able to do it. The first time you go off a jump, you can, if you know how to jump, you usually land okay, unless you do something really ridiculous, right? So this is something that computers don't do well, or robots. How about open-ended tasks? You give a kid a bunch of Legos and say, build something, you're going to get something, even if you're vague like that. Say, build a house, he'll have a house. A computer, you just say, give them some Legos and say, build something, they're going to ask you a bunch more questions. And say, well, what do you want to build? Tell me exactly the specification. Do you want a big thing, a little thing? What do you want? Kids, adults, everybody can just build something. So, what the conclusion I've come to here is that artificial intelligence is not really like natural intelligence. They're actually mirror images. So I coined a term here, hope that's okay. AI is mimicking what humans do. NI is natural intelligence, and that's what humans actually do. Okay? You see, robots are great at repetition. Humans, that's the hardest thing to do, is do the exact same thing over and over and over. If you do it a little different every time, it's way easier. They're flexible. The AI is great at data processing. The more data, the better it gets. Humans, better at instant decisions. The more data you have cluttering your mind to make a decision, actually the harder it is for you to make a decision. So it's better if you have less data as a human. Narrow tasks, that means they do one thing really well. Us, we're better at open-ended tasks. You can just tell us to do something, and we figure it out. We can do it. So turns out our whole dream of artificial intelligence replicating what brains are doing isn't quite there yet. It's doing great work, but it's not what brains do. So it's not, they're not equivalent yet. So what do we actually want out of our artificial intelligence? We're talking about a new field. It's called artificial general intelligence. AGI is the ability of a machine to learn, plan, and acquire new skills in complex environments. That's more along the lines of what humans do. So that encompasses this whole rigmarole instead of individual tasks. Right? So how do we go from narrow intelligence to general intelligence? What do we do about that? There's a couple different ways that people are coming up with to tackle this problem. One, what everybody's hearing about, and probably part of the reason you guys are here, deep learning. And I'll go into what that actually means. It means taking a bunch of data and putting it through this thing called deep learning and coming out with new things that no one ever saw before because we have more processing power. That's one approach. The other approach is, well, let's figure out what the brain's actually doing and then try to replicate it. So these are kind of complementary. Okay, so let's go through the first one, deep learning with big data. What does that actually mean? So it means that you take as much data as you can, let's say pictures, for example, as many as you can find, and put them through this program where it sorts the data into, it breaks it up into layers. So at first, you can imagine every one of these little nodes here is called an artificial neuron. And each one of these takes a pixel, one bit of data here, one little piece of data. And then this network has these connections to these other neurons, these hidden layers within here. And it sorts the data and it processes it according to features. You can have different things you're looking for, like edges or colors. and it puts it all the way through, maybe up to 30 layers of this, and in the end, you get some end response. Is it a dog, is it a cat, or is it something else? So a human will come back, this machine will make a guess and say, I think this picture is a dog. And the human goes, yes, that's a dog, you're right. Good on you. And it says, this is a cat. Okay, you worked on that one. And then it says, I think this is a raccoon. Oh, no, that's wrong. That's actually a honey badger. So you go back through and you run the data again. So what it does is it gets better over time based on how the data is sorted and based upon how humans pick the right answers for it. So the more chances it gets, the better it works. Okay? So if you only have one picture of a cat, it's going to be really hard to find a cat that kind of looks similar. If you have 1,000 pictures of the cat, then you have all these data points to work with. Or 100 million pictures of cats, which is probably more like what we have. Right? And like that's called training, when you go through and you have it pick the right answers. And then you can just set it free on its own in the end, and it'll get the right answer most of the time. And that's how the Google and Facebook facial recognition basically works. There's lots of layers. The deep is lots of different processing layers. And the learning is a bunch of statistics and other approaches that make it decide which is the right answer. So this is knowledge base. That means that every answer that you have here, somebody already knew. You're not making new information here. And so the people that have the most data, like Google and Facebook, these are the ones that do the best at this kind of work because they have the most resources to pull from. Remember, the more data, the better it works. So in the end, Google usually wins at things like this, right? So anybody have any idea what could be a problem with this approach if you really want human-level intelligence? Well, yeah, you're right. You're not going to get something that's different from human knowledge. You're not going to get better than human knowledge, right? Yeah, you won't go beyond what you trained it as. Yeah.
The other problem is I saw an example last week of something where they were feeding in houses. They were feeding in pictures of houses. And then they basically created an app that was like Tinder for house hunters. And you would select the houses that you'd like, and then it would start showing you houses that were like that. But what if I like 2 or 3 different types of houses? It's routing me down a path, and maybe there's other paths that I haven't explored.
Yeah. Or that's actually a friendly answer, but what if you have people that actually purposely give the wrong answers here too? So people like, well, not like me, but maybe like me sometimes, give the wrong answer to things like this, and then it's going down the wrong path with what the majority of people think. Or some things are specific to a specific data set too, that a general data set doesn't work for. So you'd have to have so much data that you'd have to see that there's an individual difference in this region versus this region. Okay? There's a couple possibilities. So who's doing things like this? Well, Google, as I said, uses this kind of approach. Facebook uses this kind of approach. There might be another one you might have heard of, this movie called Ex Machina. Am I saying that right? Ex Machina? I can't say it. So what they did is this guy was basically the guy who made Google, essentially, and he put all his data and all his information into an AI program and created her. And of course, that worked out beautifully for everybody. Right? So it was just a movie. Okay. Okay, so there's another approach that's coming out there, and that's using neuroscience. And one way is using the neocortex to create that data flow that you saw with the deep learning. Now, the neocortex is the outside layer of your brain. It's the newest evolutionary creation of brains. It is 2 millimeters thick of 6 layers of neurons that stack all around the outside of your brain. And it's kind of structured like this, the way they connect. Here's the different layers. They have different types of neurons in here. So they work out how these things connect, how these neurons would connect in real life, and say, okay, I'm going to make my data flow look like this. I'm going to throw a bunch of data through it, and then go through the general machine learning techniques, the statistics and the other types of techniques that change the way these neurons communicate and come out with a better way of processing big data. So this is called neurocomputing. Make the computer work like a neuron or like a brain. Okay? Can anybody think of a problem of doing this way? I mean, it's definitely a step forward. It's working towards being more like a human. There's some subtleties to this one that maybe you're not familiar. Yes?
The human brain isn't necessarily the most efficient way of doing things. So potentially the biases that we have in our own brain that we don't even know about could be replicated in our artificial intelligence.
Yeah, so that's a good point. What if what's happening here actually has to do with how hungry we are, has nothing to do with like processing an interesting image? That would add more bulk, maybe go down the wrong path. Another thing that people might not think of here is actually we don't know everything about how all this connects. We have to make some educated guesses to really get the fine detail right. And another thing that you might not know is before you even get to the cortex, there's a lot of processing that goes on. So from your eyeball, you're already starting 3 layers deep before it leaves your eye, 3 layers of neurons. There's a lot of processing that goes on. And then it gets into this abyss of the middle of your brain, the midbrain, that does a bunch of stuff that we don't even have any idea how it works. And then it gets to your cortex, which we have a lot more access to. We know a lot more about the cortex. But what's happening before it even gets there, that's going to be lost if you're just looking at the neocortex. Who's doing this? Well, there's this company called Vicarious. There's actually a few companies doing this, but Vicarious made this demo where it fed a bunch of image data, let's say, of rabbits, and their image processing was able to pick out rabbits from the clouds. So this is kind of a step forward because this isn't actually a rabbit, but it was using what they were calling imagination to kind of fill in the gap. And that program could say, oh, that's the rabbit's foot, that's its ears, he's fluffy, something like that. So they're working a little bit stealthily on the next thing. How about a different neuroscience approach? Let's say instead of just doing some of the data flow, let's just brute force this and get the whole brain into a computer. That's 100 billion neurons and 1 quadrillion connections. For those that don't know a number that big, that's 10 to the 12th connections. Right? That's a lot. This was accomplished in 2005. So believe it or not, they finally had enough computational power in 2005 to do this. What they're using is biologically accurate neural types and numbers of neurons. And they didn't just use the cortex. They used this thalamocortical model, where you actually take some of these connections from the deep brain outward and back and forth. So they had more than just the neocortex going on here. This is another type of neurocomputing approach. So can anybody think of a problem with this? Yes. Microphone?
Is this just storage or a processing model?
This is a processing model.
And so I guess I don't quite get the distinction of how the processing model works. How is that different from a regular computer, standard computing?
So the computer, there's a computer simulating this, and all it does is change the way the connections of the data go through. So instead of having a very broad, most things are connected to most things, they specifically connect certain neurons to certain other types of neurons, and they have very specific properties of each of those types of neurons. So some of them signal a positive flow of ions, let's say. They're going down to like electrical properties of these. And so they'll have inhibition or excitation and shut off the signaling from other signals based on those different types of electrical inputs. It's still working like a computer, but the way the data flows is supposed to replicate the way the brain's data flows.
So it's a different form of RAM?
Yes, except for you could have this not just in RAM. You can have it sending data back and forth to a hard drive in a similar fashion. Does that work enough for you? Okay, you can talk to me afterwards. Okay, so can anybody think of like one immediate problem here when you have something this big?
Well, one is the scale, obviously. Like to run this kind of simulation, like would take huge amount of resources, right? But,
It is.
But the other thing is that if we don't know so much about the brain, it strikes me that it's kind of like the 80% that you don't know about all this. Like
Yeah.
the way that they're connected physically, like is important, I guess. But it seems like it's really how they're connected and all the little details about how it works that we still have no idea, right? And
Yeah, so they simplified it a little bit, and they had repetitive units. So they picked a unit that they knew a lot about, and then replicated enough times so they had the same numbers of neurons. But you're missing, they missed some of the very specific differences between what happens here and what happens here. Like, it looks generally the same, but it is slightly different. Yeah.
Well, I was just kind of building on top of that is that I think that you know, as brains age and as we learn more things, a lot of pairing goes down, and so this is it almost feels like they're probably replicating like an infant's brain, and
I think this was supposed to be an adult brain.
Oh,
in this
okay.
case.
So then you're making guesses as to how that pairing process would have happened naturally. So again, I think it's a matter of probably not knowing how.
Yeah, so
the
there's,
process works.
yeah, there's still some guesses. You're not going to get exactly the right thing. I think what their main goal was to say, if we have this much processing power, the same amount as a human brain, then what are we going to get out of it? Even if it's not exactly perfectly like the human brain, should be close enough to see something interesting. So they actually built some products off of this, and they have one of their products that I thought was kind of interesting is they made this self-driving floor cleaner that could map your whole warehouse, and it would adapt as people were around and things changed. So they were trying to get the adaptive functions of the brain going on there. The other thing that they have built is they're trying to make a brain for any type of autonomous robot. So they say, okay, we can use this software and just throw it into any autonomous robot, and it should work. It should pick up the learning that the human brain type of learning like the human brain does. And that's called Brain Corporation. Okay, so there's still some problems with this, though. There's one thing I want to bring you back to the 80s on. It's kind of an idea that came out of an MIT lab. That, let's not think about anything. Let's just do stuff. And in the 80s, they had the problem they didn't have the computational power to do any of these really interesting things that we can do now. So this guy named Rodney Brooks built this robot called Genghis, where it was essentially like an insect, and it would just respond. So it would chase people around the room based on a heat signal. It would crawl over boxes. It would just work. It wouldn't get stuck in thought. So obviously the biggest problem with that is that it can't change. It's stuck with the way you programmed it. They made an interesting product later based upon this research. I think maybe you might know this. The Roomba came out of this kind of work. All right? So it just does stuff. Doesn't have to think about much. And you know there's a few problems with the Roombas where they get stuck in places because of that. They're working on more smarter Roombas now. So the last thing I want to bring up with this thing is, well, okay, big data, like you guys said, doesn't give anything new because power doesn't really equal the intelligence that we're talking about. You can get lots of things that people already know, and so it looks intelligent, but it's kind of like putting a giant engine in a car like this. It might go pretty fast, but you're not going to win races doing this. You have to have some finesse, right? And if we're just looking at human intelligence, there's a lot of things we don't know about humans that kind of limit what we can do with that at this point. We can't do the types of experiments with humans that really tell us how the brain works. That's not right. That's not ethical. And the other thing that we know is there's actually a lot of animals that do a lot of smart things, and they don't have all this neocortex. So like Garrett was saying, what if there's other ways of doing smart things? What if we're picking the wrong kinds of intelligence to replicate? Well, we would see that if we looked beyond humans. So there's another approach, and that's doing neuroscience, but with a bottom-up approach, where we say, let's figure out the underlying principles, not just exactly what it looks like on a large scale, but what's the principle of how things learn? Like even single-celled organisms all the way up to the more complicated brain. Let's look at the simplest organisms that do something intelligent and see if we can find a principle of how that works. And maybe some more of the stuff about the middle of the brain that we don't know as much about. And that's the kind of thing that we're trying to do with Brain2Bot, is build these principles so that we can scale them into more intelligent properties. And this is kind of a funny little prototype that we built that's an autonomous animal. Okay. So where we're tackling the problem is kind of the fringe of artificial general intelligence. We're out here going like, okay, we're not really doing statistics. We're not doing machine learning. Let's see how animals do it. Let's get out there in no man's land and see what we can do. Yeah?
What's KDD?
Knowledge in database discovery. Oh, what is KDD? Knowledge in database discovery. So how do you build these artificial general intelligence principles? Well, we can look at other things that other animals do. I challenge you to find an intelligent thing that humans do that's not found in some other animal somewhere. So even things that we think are really, really intelligent, like using tools, well, crows use tools. Primates use tools. What about conversation? They recently recorded 2 dolphins taking turns chatting back and forth, just like they were having a conversation. A long time ago, they did studies on chimps, and they were doing sign language back and forth. And gorillas and other primates do this too. What about navigation? We know the best way to get from point A to point B. Did you know that bees do too? That's a pretty small brain, can figure out where to go. Action planning. Did you know that spiders can plan an attack on their prey? Like they can see it on one side of a rock and then go around completely the other way and attack it from the other side if that gives them a better advantage. It's really pretty impressive for something that is the size of a pinhead or maybe a little bigger. So instead of tackling here, maybe there's something in the fly with a brain this big that we can get. So let me try to get through this a little faster. So why work from the bottom up? Well, this is a fruit fly brain. We know when we label these, we know every single neuron that we're looking at here, what its identity is, who it connects to, and even some of the signaling properties. We can control those cells and make them behave differently and see how that affects their behavior. We can do genetics and find out all the genes involved with this. So we can do things with these organisms that we can't do otherwise, with these really small, intelligent creatures. Did you know that single-celled organisms can learn? So today, there's no biological principle of learning that works on artificial intelligence. So we actually created the first biologically plausible algorithm that can be used for robots. And we did it starting here. So if we want to get to AGI, we better figure out how the brain learns on a molecular basis. Priorities. This is something that robots are starting to have now, but did you know that when you're playing, you act differently with your friends than when everybody's scared? Bet you knew that. It's a whole different brain state, same stimuli, different type of thing going on here. We want the robot to respond intelligently that way too. Fruit flies, you can give them an odor in the morning and pair it with food. They know that's food. You can give them the same odor in the night and shock them with an electric shock. And in the morning, they'll go towards that odor for food. In the evening, that same odor, they'll run away from it. They know the difference between the same odor in the morning and the night. That is unbelievable. And furthermore, we know the circuitry involved in that. So we can figure out how to replicate that kind of thing on a AI level. So this is something specific for the Truckee crowd here. Think about that with driving in the snow. Same signal, deer jumps out in front of you. Do you want somebody training this in the Bay Area where they slam on the brakes, or do you want somebody giving a context-specific learning where you actually know what to do with that up here when it's driving in the snow? Did you know that wasps can facial recognize? Humans even. They can recognize their own faces, but they can recognize human faces. So you ever wonder why wasps are attacking you specifically after you went after them? You might have to do something with this. And this is learning how that works as a way of getting to a point where you can use less data to do facial recognition. Variability. Different birds have different bird songs. They're unique. They're mostly copies, but there's a little bit of individuality. Let's put that into robots to get creativity. How about musicians? Any musicians here? Yeah? You play the same song 20 times? Is it always exactly the same?
Not exactly the same, but I try.
Well, I would argue that playing it differently every time is actually a skill. And the best musicians can play the same song backwards and forwards and different tempos and different feelings. Robots can't do that. So let's figure out how to get that non-stereotype behavior. Again, bees with navigation. It would be really nice to be able to have unconnected devices being able to work on their own, not have to have GPS all the time. Right? That's a safety issue. Did you know that humans are not always the smartest creature? Sometimes other animals are better at stuff. Squirrels can remember more nut locations than we can. So if we're trying to get the top intelligence, it's not always the human we're trying to go after. One thing to think about is, like, why do some of these animals have such big brains? This is a little fish. It's got a brain with the same body to brain ratio as a human. Why would that be? Why does this dolphin have a bigger brain than we do? There's more neurons just in its cortex than us. We don't know why that is. Maybe there's a reason. Want safety? Well, we better start endowing moral judgment, emotional connection, and efficiency into our robots. And that's all a neuroscience thing. You know that smart machines are safer than dumb machines because you've seen this in humans, right? So why is this important? so that robots do not light firecrackers at us, and also so that we make AI that we can actually relate to and doesn't try to kill us, but not only that we can learn from. There's a lot of problems that we have today that we already know the answers to, but we're not listening to the people who know the answers. So why is that? Well, it's because we're not communicating it properly, and we're going to have the same problem with our robots if they don't communicate what they can teach us well. And that's also a neuroscience question. So this artificial intelligence has to work for everybody, or else it's going to be a problem. And the way to do that is to be able to have it actually be efficient and show everybody how it can work for them, even people who don't want to be in this tech industry. So that's my take on it, as I think neuroscience is the best strategy to get to these parts, because we already have this stuff inside of us. Let's just try to replicate some of it. And last thing, we might just have to understand these more complicated creatures, maybe the most complicated thing in the known universe, in order to get to this AGI. But we also need to understand the building blocks of how this works all the way through to really make this work right. So that's all I've got. So thank you very much. And I'd like to hear any questions.
Thank you. I'm sure there's still questions, and here are the mics that capture the questions.
I can yell it out.
Actually, no, it's about the online.
Recording, yeah.
Hi. Can anyone hear me?
Yeah.
What is your business model?
I thought I was giving an intellectual talk. Yes. So the business model is to figure out the basic principles of neuroscience and put them into products along the way as we get towards the bigger intelligence questions that we're tackling. So first thing we're going to do is make a robotic toy that is efficient. It doesn't have to be cloud connected, but it still acts like a real animal. It learns, it has different personalities, and it interacts with us on a personal level. So we don't have to learn all of the, we don't have to get all of this AGI right first, because if it accidentally bumps into you once, it's not as big a deal as crashing a car, right?
Is the technology that you develop going to be then licensed to other companies to build products then?
Yes.
Okay.
Yes.
Thank you.
Right behind you.
Is there an active like hardware or sensor component that can kind of tap in and feed some of this
So there's
the AI knowledge? So like, you know, if X then Y. And
yeah, so there's kind of two ways of going about it. You could have everything abstracted down a layer, which is the way that we're doing it, where you could have any sensor input and it feeds into a neural system. So each neuron can deal with different types of data. And therefore, you could connect any type of sensor up to it and make it sort through and do what it needs to do. And then in the middle, you need to have some way of dealing with it. So you have some programmed responses and some learned responses and have a combination of them come out.
Gunnar, my question goes back to the one you had about the neurocomputing showing the adult brain, and someone said it'd be like almost an infancy, and I think Gil had mentioned as well, is that every brain, everyone in this room has different experiences. We've all learned off our experience that we're going to react differently. For like if someone also near a loud noise, we may all react differently, thinking, oh, that's a gunshot, that's a backfire of a car. So how can they make one brain that's going to be able to be so able to handle all those reactions collectively through, say, a community, say, a region? Because people, again, growing up in North America versus someone growing up in Europe, again, there's so many differences that as people grow, how do they kind of grab all that?
So yeah, that comes to the core problem of the deep learning. The idea is to be able to get enough data to be able to get everybody's individual differences and a statistical approach to say you're most likely to be in this category that most likely would say that you've had this type of experience and therefore you should respond this way. The reality of it is that, like you said, every single person's different, but you can make a flexible program. So in principle, you could have a brain that you just put it into this environment and learns all those things the way that you would learn, and you could come close enough to Steve to say, oh, okay, that's Steve, he's just a little off today, right?
Thank you.
Yeah.
I guess my question was, do you want to do that? Do you want something that could be so variable, or is the idea, if you're building an artificial brain to put into different products, do you want the perfect brain? Do you want to build something that is, okay, if we removed all these flaws and edges of how we do things and find the right way to do it?
So yeah, that would go with two different philosophies that are appearing. There's the people that say, well, like one size fits all should be good. But the reality of it is, even in your own brain, different parts of your brain, though they look very similar, actually have slightly different structures. So you could get a program that could deal with sound, it could deal with your visual experience based on the same program, but a human brain has its sound processing slightly different than its visual processing. So you want these individual differences to appear even within your own brain that are going to be tough to do with a big approach like that. So.
Comment here.
Yeah.
Of course, any type of intellectual component here is going to have the room for corruption or viruses, and you build a good robot, it becomes a bad robot.
So for right now, that's a long ways off. So that's not necessarily something we have to get right today, but 10 years from now, you're probably right? So what do we do to avoid that bad robot situation? And the way that the AI leaders are trying to do it is to make this available for everybody. So have as many people come into this AI collective as possible and say, okay, how do we safeguard this from everybody by having everybody have a say in it? So that therefore, like computers today, you have a lot of programmers that know how to fix viruses. And the same thing would be with AI. When one bad programmer goes off and tries to wreck everything, someone else fixes it. Yeah?
A follow-up question in that direction is, you're talking about general intelligence as the next goal. Once that is achieved, what people are talking about is superintelligence that would actually go way beyond of what we
Like
we
squirrel
can do.
intelligence, yes.
Yeah, or squirrel intelligence, yeah. That's the nut intelligence. So what do you see as a time scale? Is this something that we need to worry about in 10, 20, 30, 40 years, where things can all of a sudden take off on its life on its own and become dangerous?
I think it's more than 20 years out. And once you get out to that region, it's all anybody's guess. The reason I don't think it's immediate is because I think by principle, the paths that the majority of people are working on can't get that level of superintelligence that you're talking about. Because most people are trying to optimize for specific tasks. That is the opposite of something that can take over the world with any way it feels like it. Right? So you might have one that can shoot off nuclear weapons that we'd have to deal with, but to be able to infiltrate all of humanity and figure out how to build a nuclear weapon on its own and then to go do something with it, that's not the kind of thing that we have the ability to do in the near future. So I think it's a ways off.
Has anybody applied genetic algorithms over the top of this to try to optimize certain areas?
Yes. In fact, that is a big focus on, there's a couple companies doing that. I'm trying to think of the name of the first one that Sentient, I think, is one that's doing that. That'll speed up the process significantly because you can just have it running in the background and selecting things that people don't want, selecting out the things that people don't want. But again, you come back to the principle of it is like that's still, you have to change the entire structure of the program to get to the type of intelligence, and evolution isn't very good at starting from scratch. Usually it builds upon itself, and I'm talking about starting something from scratch to get artificial general intelligence. I think that's what you have to do. Yeah.
Well, I'm just thinking about how the brain is a neurochemical system. And in addition to the electrical signals, there's a variety of different chemicals, dopamines and serotonins, that all work on the same nerve. So that starts to create almost an infinite number of permutations between electrical signals and chemical signals. And I was wondering if you're thinking about how that chemistry can also play into this.
That's actually where I started. So I'm a molecular neuroscientist, and when I was talking to some of the people about not seeing the principles of what I was learning going into AI, I'm talking about molecular principles. Really, like everybody knows that they're a different person when they're hungry, right? A lot of that is a chemical signal, and that kind of thing is not being replicated well in AI. So yes, absolutely have to get that part right. I think she had her hand up first, so can you get her and then?
So kind of along the lines of the whole molecular part, so a single-celled organism doesn't really have a brain, so when you're saying you want to understand it, are you looking at what it's changing, like what genes it's expressing? Is that what you're trying to understand, or what are you saying when you want to start with the single-celled organism?
Exactly. Thank you for bringing that up. I kind of glossed over that. We're talking about the molecular networks that are inside this. You're right, there are no brain cells. This is one cell. A brain cell is bigger than this guy. This has molecular concentrations going up and down, and the way that those interact is how it changes its behavior. So we're talking about building a principle of how molecules change their signaling properties to change behavior. We start here and then work up. It's different from the electrical properties of the neurons that change, definitely.
On the hardware side, are you just using general computing chips, or are you using some sort of special purpose chip? What are you doing there?
So this is actually the first argument I had with Bill, my CTO. So I said, I want something parallel, and that doesn't really exist maybe. And he said, well, let's start with something that works. So we took an off-the-shelf chip and started building it with that in mind, that we can build stuff with off-the-shelf parts the way that chips work now. I think in the future, it's going to expand, and hopefully we'll get some new technology like these neurochips that will just accelerate our process.
What would you say is different about your approach as opposed to like the founders of AI, like Turing or Moravec? Is it more of are you focusing more on the learning-based aspect, or leveraging the big data, or is it problem solving? And because all the classic guys thought more like engineers and problem solving. How do we break a code, or how do we solve a problem with AI? Or would you say yours is more of a learning base, or is it more like emulating a person?
So I'd rather emulate a brain than try to say, let's make a computer that kind of acts like a brain. I want to say, like, what's the principle of the way the brain interacts? It's not necessarily data processing the way people think about it. They don't just take in data, process it, and then make an output. There's a finesse that goes on where it's dealing with change. It's dealing with relative amounts of things. It doesn't say there's a specific, this pixel is 237, whatever the number is. It says, oh, it's a little more gray than the one next to it. So that really you have to have a different approach when you have to think like a biologist rather than a computer scientist, I think, to really get this right. And that's what we are trying to do. Yeah.
Just back to the parallel computing thing, doesn't cloud computing give you the scale to model this stuff?
It does. The scale, yes, it does give you the scale to do it, but we have to get the principle right to get the scale right. So like I said, with a fast car, you can put all the power you want, but if it doesn't have the ergonomics, you're going to go off the corner. So I want to put the ergonomics back in it and then get to a faster car.
So speaking of cars, one of the big things now, of course, with AI is, putting the moral perpetuity in there. Like, so if a car is going along, there's 3 kids in the car and 4 kids cross the street, what does the car do? Does it hit the 4 kids in the street, or crash the car and hurt 3 kids in the car? I mean, how are you going to handle something like that, or do you have a way to handle something like that?
Yeah, so we're going to invent a way of bubble foam that throws everybody out of the car, and the car disintegrates. But in the short term, most of the time, we're not even to that question yet with self-driving cars. We still have to keep the car on the road for the whole day. So the first thing we have to tackle is, can we get the car to identify that those are children? That's hard. I mean, when you're going, yes, it might see the children, but then you have to say, like, well, how do you know it's a child and not an adult? Okay, well, you can kind of do that, yeah, but how many times in your day are you going to actually run into a field of school children that are actually trying to commit suicide, as the time where the deer's walking across the street and your own crash will kill you too? That's the kind of thing that we never actually deal with in real life either. The main thing is, how do we get to drive safely first, no matter what the obstacle is, and then work on the nuances of morals. So the moral question is, in the region that you live in, what is the appropriate response? Not in general, but in some places, it might be more appropriate to run over children than it is to run over adults. I don't know. So I don't know. That might happen. But that's a very specific question for a very specific set of people. And I don't think that just saying, like, okay, let's throw this to everybody, you're going to get a different answer from everybody. So there isn't a good answer for even human drivers for that yet. So I think you have to go to, like, what are people going to actually buy at that point? But first, let's get the car to stay on the road first. Yeah.
So we have a question from the other room. How far is Brain to Bot from a working prototype?
We have a working prototype. It learns. It adjusts its personality if you want to. You can have ones that are scared, or ones that are happy all the time, or ones that love you a lot. They show it very basically, don't worry. It's, yeah, so we have one that it drives, it can eat, it can actually poop, it can interact based on the different sensor inputs that you bring to it. And right now we're working on finishing that software up and then designing actual looks-like prototype for going to market.
Do you have an estimate for how far you are from market?
It depends on who we can get to partner, because we either need a partnership or more investment to actually take it to market. So if we get an investment in the near term, we would like to go to market next year, like have it by next Christmas.
So imagine a Truckee where instead of all those barking dogs running around when you're on the streets, there are all those smart doggy bots. And I'm not sure if this is kind of the future we all want, but it sounds interesting. And I am sure that it will take several decades before we replace you as a speaker with a bot that is standing here and
well, you could do that now.
But we have preferences. So thank you so much for being here and for this exciting talk. There is also this question about how far is the prototype, and we've learned that for those who are actually in this room, there's a little bonus that you only get when you are in this room. Is that correct?
Well, yeah, if you want to see a small taste of a video demo that we created, you can have a look and see a couple of the functions that we put into it.
Yeah. So thank you.
Thanks.
Yeah.
Appreciate it.
Fascinating.